Hi, this is Dr. Nick from the ECG Academy with the final chapter in Section 3, talking about the electrical activity of the heart. And we're talking about the electrical events and where the ECG comes from. It's a review of the cardiac conduction system, but we're going to finally get to look at a real ECG signal and what it looks like and how to name some of the parts of the signal. So this animation was something I put together showing the electrical activity of the conduction system and how it relates to the heart function. But let's get rid of that because we want to take it one step at a time. So I'm going to shorten up, I'm going to close this up so that we can see this animation. It's an illustration of the heart with the right atrium and the left atrium, the two ventricles on the bottom, right side and left side. And the cardiac conduction system is drawn in dark blue. Remember that the sinus node is located in the top of the right atrium, and it borders right where the superior vena cava attaches to the right atrium. The sinus node here, as you can see, is drawn with little blue-like projections, little finger-like projections. In fact, the sinus node is a clump of cells, a large clump of cells, but it's a complex structure, and there are extensions of the sinus node that stretch out into the atrial muscle to sort of connect the sinus node with the atrium, and it helps conduct the very low-level signal that the sinus node generates. The sinus node, in fact, generates a signal that's so tiny that we really can't pick it up from the outside. If you do a cardiogram, you cannot see the sinus node function on a cardiogram. You can only indirectly get a sense of what it's doing. But if we put a wire into a vein and thread it up to do a recording of the inside of the heart, we actually can manage to record the sinus node, so we kind of know how it works. Well, the sinus node, as I said, is connected by these finger-like projections to the atrial myocardium, and if everything is working properly, what will happen is the atrial muscle will pick up that signal, and it will conduct the signal across both atria. Now, the atrial muscle is, as I talked about in the heart muscle cells, they're connected. And so you get this bucket brigade action that connects cell to cell to cell, and you get this rapid conduction or propagation of the electrical signal across both chambers. Are the two chambers connected? Well, behind the aorta, there is a bundle of muscle that is known as Bachmann's bundle. And it takes the electrical signal from the right side and kind of easily conducts it over to the left. So there is a connection behind there. Now, when we're doing a cardiogram, we can see the atrial activity because what shows up on the cardiogram is a bump. Now, it's a thin-walled structure, so it doesn't generate a lot of electricity. But we see a little bump, and that atrial activity is known as the P wave. Now, the signal gets into the AV node, which, as you recall, is the electrical connection between the two chambers. The AV node is another specialized structure that delays the signal for a split second, but then conducts it down into the Purkinje system, down the main bundle of His, the bundle branches, and the Purkinje fibers. Let me show you what that looks like. So those Purkinje fibers are designed to very rapidly conduct the signal down into the ventricles. Now, can we see this on the surface ECG? The answer is no. We don't really see AV node conduction, and we don't see Purkinje system conduction. We can record it from the inside, and if anyone's ever heard of a His bundle electrogram, that is a technique where we can put a wire into the heart and record the electrical activity of the AV node in the bundle of His directly. That's what electrophysiologists do when we're interested in studying the electrical system of the heart. But in the cardiogram, you don't see much of anything except the AV node delaying the signal for a split second. You do get kind of a flat section here that goes on for a split second. Now, when the Purkinje fibers fire, the ventricular myocardium gets the signal. And then the ventricular myocardium fires, you get action potentials, just millions and millions of them, and that's what generates the ECG signal from the ventricles. Now, when the ventricles fire, there's a very characteristic appearance to it. It looks like that. And most people would recognize that as the signal that the heart gives off when it beats. We refer to this as the QRS complex. And I'm going to get into more detail about how we name the QRS complex. But notice that these ventricular cells, they fire when that turns bright white, but then they reset themselves. There's depolarization, which is what the QRS complex represents. But then the heart muscle cells have to electrically reset themselves, and that's what repolarization is all about. If you remember the cardiac action potential, I know you don't want to think about it because it was kind of confusing, but the cardiac action potential, you have this sodium rushing into the cells, and that causes depolarization of the heart muscle cells. Remember, this in blue is just one single heart muscle cell, whereas the ECG here is the whole entire heart. But after a while, those cells repolarize. They go back to that negative on the inside kind of, you see, if we draw this as 0 millivolts and this is minus 90, I know I don't want to bring this up because it was a bad memory, but when they repolarize, you can pick that up, and it results in a bump that's referred to as the T wave. Okay, so let's get rid of this action potential. We don't need to spend too much time with that right now. We're really talking more about the QRS complex and the P and the T wave. Okay, so now what part of the QRS is the Q and the R and the S? It's very simple. The first downward deflection of this signal, the first downward deflection that occurs during ventricular depolarization is known as the Q wave. Following the Q wave, the next upward deflection is known as the R wave. Okay, and then if there happens to be another downward deflection following the R wave, then that is known as the S wave. Now, why is that so important that we name it that way? It turns out that not every QRS complex looks like that. When you start getting involved with reading 12-lead ECGs, you'll find that some QRS complexes look completely different. In fact, in some certain circumstances, the QRS complex, you may get a normal P wave, but the QRS complex may look like this. Now, wait a minute. Isn't that something? There's something wrong with that because it's upside down, isn't there? Well, no, it turns out it's not upside down, really, because sometimes the QRS is up and sometimes it's down. But how do we name this part of this QRS complex with this very strange kind of appearance? Well, what is the first upward deflection called? Remember, the first upward deflection is the R wave. So this is the R wave. There is no Q in this ECG recording. That's the R wave. And then you have an S wave here. Now, what if you had something that looks like this? Well, would this be any different? Actually not. In this case, what you have is there's no Q, okay, because there's no downward deflection that starts the QRS. Remember, the Q is the first downward deflection. You have an R wave, big tall one, and then you have an S wave. Well, what's the difference between this RS and this RS? It's only the ratio, the size difference between the R and the S wave. And some people use a kind of a shorthand to describe how the QRS appears. And in this QRS complex, you have a tall R and a little s, and some people will write it this way, as big R and little s, whereas this QRS complex would be written as a lowercase r and a tall s. That's how we name these signals coming from the ventricle. So it can look all different. It can look crazy. These two signals have no Q wave. All right, let me draw another one. This one's going to look completely different. It has a P wave. But wait a minute. There's no upward deflection at all. So in this case, there's no R wave at all. But if there's no R wave, then what do you call the downward deflection? Is this a Q? It's the first downward deflection. Or is it an S wave? Well, it's not really an S wave because there's no R, and remember, S always follows R. So there's a special name for this kind of ECG signal, and it's actually known as a QS pattern. What else can we see? Well, it's not uncommon to see an EKG where there's no S wave. So this would be the Q wave, and there would be an R wave here, but no S. So it's a little Q, big R, and you would classify that to look like a lowercase q and a big R. You could also have a different kind of QR pattern. You can have a deep Q and a little r. And this would still be in keeping with our naming convention, but in this case we'd use a capital Q and a small r. So you can see that the QRS can look different under different circumstances, but I want you to just learn the naming convention because it's important when we start to identify abnormal waves in the EKG. Well, there are a couple of other parts that I didn't talk about. First of all, this flat part that follows the P wave, that's sometimes known as the PR segment. And we can actually measure the PR interval, which is a time interval from the beginning of the P wave to the beginning of the QRS complex. So we'll measure this in subsequent lessons as the PR interval. Okay? Now there's a Q wave, there's an R and an S. We can measure the duration of the QRS complex. This point right here, where the QRS ends, is known as the J point. And the flat segment that follows the J point before the T wave starts is known as the ST segment. Okay, and ST segments are very important when we start to try to diagnose ischemia or infarction, because then what you'll sometimes see, for example, in ischemia, the ST segment will become depressed compared with the rest of the signal. So this is where the ST segment becomes important in diagnosing underlying heart muscle conditions. Finally, the last interval that I didn't mention is known as the QT interval, which is from the beginning of the Q wave to the end of the T wave. And I'm just mentioning this, but when we get into the chapter on the actual measuring these intervals, we'll be able to make certain diagnoses based on the measurements of these intervals that we'll do with a real ECG. So that's an overview of the electrical events of the heart and how these events relate to the cardiac conduction system, how we name the squiggles that come out of the heart when we record them on an electrocardiogram, and the different shapes and configurations that we may see when we start to analyze these ECGs. So that's it. Thanks for watching, and remember to log in to the ECGacademy.com for more videos from beginning to end, basic to advanced, so that I can help you become an ECG expert too.